Okay, so the current scheme of in the current scheme of things, we are still in section 10.2, which we will finish today, and that the rest of what we have to do is one topic. We covered arc length last time. Now we got to cover surface area. So okay, so we are covering surface area now from the point of view of parametric curves. So remember, we took a curve and we rotated it around, say, the x-axis. And if you go back to when we covered surface area, the surface area of the surface of revolution is given by, so the curve is defined from x equals a to x equals b. And if you remember what the formula was, it was the integral from a to b of 2 pi y ds, where ds is the square root of 1 plus dy dx squared times dx. And y is viewed as a function of x, so y is a function of x in this formula. Okay, so we can just take what we just got and replace x by its value in terms of x of t and y in terms of y of t. And let's say t is going between two numbers, alpha to beta. So now let's just do the substitution. The only thing we have to do is take ds and rewrite it. Now, last time we saw that this ds was the same thing as dx dt squared plus dy dt squared. So it's going to be x prime of t squared plus y prime of t squared. And then dx is given by x prime of t. Oops, I didn't say that right. It should be dt. We did this last time, so I'm not going to go through the derivation again. So if we do the substitution, we're going to get that the surface area of a surface of revolution of a curve given by a parametric equation is going to be the integral from alpha to beta. Those are t limits of integration of 2 pi. Y is, of course, y of t times the square root of x prime of t squared plus y prime of t squared dt. And that is the formula we're going to use to do the calculations with. And again, having that square root there is going to make it somewhat difficult to actually do many of the integrals which arise. And so the book has to choose the examples very carefully. Okay, so as a warm-up problem, let's do a calculation we did before, but it'll be easier to do from the parametric point of view. That is a sphere of radius a. So what I'm going to do is I'm going to take a semicircle given in parametric form of radius a, and then rotate it around the x-axis. And the semicircle of radius a is x equals a cosine of t, y equals a sine of t, and t is going from 0 to pi. So we can now just apply the formula. The surface area is going to be given by, so first of all, we have to calculate x prime of t. That's negative a sine of t. We have y prime of t dt. Y prime of t is a cosine of t dt. So x prime of t squared plus y prime of t squared, which is what we're going to need in that square root, is negative a sine of t quantity squared plus a cosine of t quantity squared. And if you factor out the a squared, you get a squared times the sine squared of t plus the cosine squared of t, which is 1. So the surface area is the integral from 0 to pi of 2 pi. The y is the a sine t. And then we have the square root of a squared. That was what we just calculated, and then we have dt. In other words, it's, if we factor out all the constants, it's 2 pi a squared, the integral from 0 to pi of 2 pi a squared times integral from 0 to pi of sine of t dt. So that's going to be given by 2 pi a squared times negative cosine of t, evaluated from 0 to pi. So that's 2 pi a squared times, the value at pi is -1, which is +1, minus the value at 0, which is -1. So this is going to give me a 2, an extra factor of 2, so you get 4 pi a squared. So that is the calculation for the surface area of a sphere. So in my second example, I'm going to do a more substantial problem. It's going to be x equals t cubed. This is from the exercises, I believe. Y equals t squared, where t is going from 0 to 1. You'll see that the integral is a little more complicated in this case. So, what is x prime of t? That's 3t squared dt. And y prime of t is equal to 2t dt. Okay, so by the way, this curve can be viewed as y equals x to the 2/3 if you do the substitution. So that's a curve that looks something like this, between 0 and 1. So we're going to rotate it around to get a surface of revolution. It looks like the part of a horn or a bugle. Okay, so now let's compute. The surface area is the integral from 0 to 1 of 2 pi times y is t squared, times the square root of the square of x prime of t, so that's 3t squared quantity squared, plus y prime of t quantity squared. Oops, there's no dt here. This is x prime of t and y prime of t. So 3t squared quantity squared plus 2t quantity squared dt. Okay, and you're left with something that looks like a bit of a mess. However, we can factor out from the integrand. Let's first expand the integrand. So the integral from 0 to 1 of 2 pi t squared times the square root of 3 squared is 9, t to the 4th plus 4t squared dt. And if we factor out a t to the t squared from the integrand and bring it through the square root, that gives me an integral from 0 to 1 of 2 pi times t cubed times the square root of 9t squared plus 4 dt. Now I'm going to bring out, just for my own simplification, I want to bring that 9 through the square root. So that's going to be an integral from 0 to 1 of 6 pi. So I brought the 9 out at the expense of square root of 9 is 3, t cubed, the square root of t to the t squared plus 4/9. And 4/9 is 2/3 quantity squared dt. And the reason I'm doing that is I'm going to do a substitution to do this integral. So let me save this slide and work on another slide to do this calculation. Okay, so I'm going to clear the screen. Okay, so it's going to be we're interested in calculating the integral of 6 pi t cubed, the square root of t squared plus 2/3 quantity squared dt. And I'm going to calculate the indefinite integral. It'll be easier for me to do it that way, and then I'll go back. Okay, so the first thing I want to do is I want to do the trig substitution. T equals tangent, 2/3 tangent theta would be the correct substitution. So dt would be 2/3 secant squared theta d theta. Okay, so then what do we have? We have the integral of 6 pi t cubed, so that's going to be 2/3 cubed tangent cubed of theta. That's from the t cubed. And then the square root of the sum of the squares. So if you do the substitution and put it in, and then take the square root, it becomes 2/3 secant theta. That's what the square root becomes. That's the whole point of the substitution after all. And then the dt portion is 2/3 secant squared theta d theta. Okay, let's group the like terms. So we have, let's bring the constants out. So we have 6 times 2/3 to the, it looks like the 5th power. 6 times 2/3 to the 5th power times pi. And we have tangent cubed theta times secant cubed theta d theta. And I believe that's correct. Okay, so now we have to do this integral. Okay. So if you recall how we do these integrals, so first of all, let me put back let's put the constant back. So 6 times 2/3 the 5th power. So what we're going to do is we're going to break off a secant theta and a tangent theta. And then what's left over is a tangent squared theta times a secant squared theta. And so then we're going to convert the tangent squared into a secant squared minus 1. So what are we going to get? We're going to get, and there's a pi here I'm missing. So 6 times 2/3 to the 5th power times pi, okay, times the integral of secant squared theta minus 1 times secant squared theta times secant theta tangent theta d theta. In other words, and this term would be, if we expanded it out, it would give us a secant to the 4th theta minus secant squared theta. Okay, so we're going to let x equal secant theta, and then dx is secant theta tangent theta d theta, or maybe we should use u here, not x, because we've already used x in some sense in the problem. So then this integral becomes the integral of 6 times 2/3 to the 5th times pi, the integral of u to the 4th minus u squared du. And this becomes, after integrating, 6 times 2/3 to the 5th pi times u to the 5th over 5 minus u cubed over 3, and then there's a plus c. Okay, so that's what it is in terms of u, and now I have to go back and get it in terms of theta and then back in terms of t. So that's what I'm going to do now. So we need to, first of all, isolate the important substitutions. U is secant theta and t is 2/3 tangent theta. These are the two important things. The rest I can erase. Okay, so the stuff that's surrounded by green, more or less, is the integral expressed in terms of u. Now we have to convert u into secant theta. So I'm going to do that over here. So it's 6 times 2/3 to the 5th power times pi. Okay, so what do we have? We have secant, in brackets, we have secant to the 5th theta over 5 minus secant cubed theta over 3 plus c. And then we obtain, when we go back, and remember that t is 2/3 tangent theta, so that makes let's leave it in terms of theta for now. We now have to express everything in terms of t, so we need a right triangle. So tangent theta is 3t over 2, I believe. So 3t over 2, and then the hypotenuse would be 9t squared plus 4. Here's theta. This is our right triangle. So we get 6 times 2/3 to the 5th pi times, so secant theta is hypotenuse over adjacent, so we're going to get 9t squared plus 4 uh, uh, over 2, the square root of 9t squared plus 4 over 2 to the 5th power over 5 minus the square root of 9t squared plus 4 over 2 to the 3rd power over 3. Okay, plus c. All right, so let me box that off. Okay, this is a big mess, but we're going to have to go back now and substitute that into the integral that the result of the integration. We had limits of integration on this because we're computing a surface area. So we have to remember where t is going from where to where. So let's go back and look, because we're many slides away right now. Okay, so that slide is so far away I can't even find it, but we have to recall that t is going from 0 to 1. That was the assumption in the integral. So we're interested in t going from 0 to 1. Okay, so and so therefore what I'm going to do is evaluate what's in the yellow box from 0 to 1. So to do that, I need to erase. So we're going to evaluate this from 0 to 1. Okay, so what a horrible mess this is. But so it's I don't want to do this. It's such a pain, but I will do it anyway. Let's see. So 6/3 the 2/3 to the 5th pi. We plug in 1. What do we get? We get square root of 13 over 2 to the 5th power over 5 minus the square root of 13 over 2 to the 5th power over 3. There's probably a much easier way to write this, but this is not so easy to do when you're on an iPad, and you didn't write it down beforehand. And then when we plug in 0, we're going to get the square root of 4 over 2, which is to the 5th power. So that's 1. So that's 1/5, and then we're going to get minus minus 1/3. Okay, this can of course be simplified, presumably, but this is actually the final answer to the question in some form. What a mess. Anyway, that's all I'm going to do for today, and I thank you for your patience.